Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light or spectra. For example, ordinary table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a flame. Meanwhile, the white light of the sun was also being examined closely. And in 1802, it was discovered that the solar spectrum itself had tiny gaps. There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. This is analog. This is digital. This is analog. This is digital. This is analog. This is digital. If it is continuous, it is analog. If it is granular, it is digital. The current trend in audio, video, and communication technologies is to go digital. Instead of a continuum of color in video devices, we are limited to some finite number of colors. Instead of a continuous picture, our photo is divided into pixels. Instead of just any frequency in audio, we are limited to specific steps. This is very much like the universe in the realm of the small. The entire universe went digital about 14 billion years before we thought of it. Space, time, energy, momentum are all granular. There are only certain specific values allowed, and this granularity is accurately described by quantum mechanics. It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus. Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed. In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton had firmly established that light could have the characteristics of both a wave and a particle, de Broglie suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive interference of the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant. A true giant of quantum revolution was Werner Heisenberg. And from the vagueness of positions of electrons in de Broglie's standing wave orbits, he drew a tremendous insight which he stated like this. The more precisely the position is determined, the less precisely the momentum is known, and vice versa. And while it may sound like a bunch of gobbledygook, it was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. an electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximum are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. While all important ideas necessary for quantum theory were established before him, it fell to the genius of Erwin Schrödinger to develop the equation that correctly describes the motion and behavior of all things this tiny. While Bohr and de Broglie managed to describe the hydrogen atom, Schrödinger's equation was able to describe hydrogen with the same detail. And then, it could go far beyond. It manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms and all the elements in the universe. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world. So this is a very good picture of a hydrogen atom with an electron in the lowest energy state. The electron occupies a cloud instead of an orbit. But it spends most of its time at the radius predicted as an orbit by the Bohr model. It also spends most of its time possessing the energy that an electron in that orbit would have. But of course, the atom is not always found in the lowest energy state, as there are other orbits allowed in Bohr's model. There are other higher energy states in the quantum mechanical hydrogen atom. These states are defined primarily by the quantum number n that we talked about earlier. And for each state, the electron has a different energy, which results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, the shape can take two forms, although both shapes have the same energy. One is a double spherical cloud, one sphere inside the other, while the other shape for n equals 2 is in the shape of a dumbbell. For other values of n, the shapes can be pretty strange, like this torus plus dumbbell shape. Now the only components making up the dynamical state in the atom is the shell it occupies, and another property that electrons have called spin. You can think of electrons as little spinning tops if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that two and only two electrons can occupy each shell in an atom, one with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place.
The quantum theory emerges around 1900 because there was a crisis in physics of monumental proportions.
A crisis.
A crisis. New phenomena were being discovered that violated Newton's laws. Madame Curie, for example, refined something called radium. Radium had this magical property of glowing in the dark. Energy was coming out of nothing. Particles were coming out of nothing. That violated the conservation of energy. Energy was coming from nowhere. Around 1900, people thought that energy was continuous, that you could cut electricity, magnetism, you can cut it into finer pieces without end. And yet around 1900, Max Planck, the great physicist, had the audacity to say that energy occurs in packets called quanta.
And why did he say that?
Because if you assume that light comes in these packets, then you could explain all the different kinds of phenomenon that we were seeing, that at the fundamental level, at the level of the atom, there was a quantum effect, that energy was occurring in packets. This also meant, by the way, that matter has wave-like properties.
And this is what we call quantum mechanics?
That's right. Now, that's not the way the universe was supposed to be constructed. The atom was like a bowling ball. How can a bowling ball have wave-like properties? Well, in 1925, Erwin Schrödinger, an Austrian physicist, finally writes down the wave equation governing the electron. This is one of the greatest achievements of the human intellect. All of a sudden, we can now peer into the atom itself.
And so we're talking about atoms are waves, atoms are particles, but there's an uncertainty associated with them, right?
That's right. Then a few years later, Max Born, a colleague of Albert Einstein, made the fateful step. The question was, if matter is a wave, then what is waving? Max Born said, what is waving is the probability of locating it at any given point. We sometimes give our graduate students the problem. Calculate the probability that you will dissolve and you will rematerialize on the other side of a brick wall. Now that's absurd. How can you wake up in the morning and wind up on Mars? How can you go to bed and wind up on Jupiter? That's crazy. And yet you can calculate the probability of that happening.
It's probably low.
It's very low. You would have to wait longer than the lifetime of the universe. But for electrons, it happens all the time. That's what we call electronics. All the modern marvels of the electronic age and laser beams and microchips ultimately come down to the fact that electrons, you don't know where they are, they can be two places at the same time. How can that be? Two places at the same time? Because you don't know where objects really are. This caused so much problems that even Einstein finally broke with the quantum theory. And he said that I cannot believe that God plays dice with the universe.
With all of its weirdness and built-in uncertainty, quantum theory remains the best model of the subatomic world we have.